In mathematics, Horner's method is either of two things: an algorithm for calculating polynomials, which consists of transforming the monomial form into a computationally efficient form, or a method for approximating the roots of a polynomial. The latter is also known as Ruffini-Horner's method. These methods are named after the British mathematician William George Horner, although they were known before him by Paolo Ruffini and, 600 years earlier, by the Chinese mathematician Qin Jiushao. Description of the algorithm. Given the polynomial where are real numbers, we wish to evaluate the polynomial at a specific value of, say. To accomplish this, we define a new sequence of constants as follows. Then is the value of. To see why this works, note that the polynomial can be written in the form thus, by iteratively substituting the into the expression. Examples. Evaluate for. We use synthetic division as follows. X cubed x squared x 32 minus 62 minus 1606 2025. The entries in the third row are the sum of those in the first two. Each entry in the second row is the product of the x value with the third row entry immediately to the left. The entries in the first row are the coefficients of the polynomial to be evaluated. Then the remainder of on division by is 5. But by the polynomial remainder theorem, we know that the remainder is. Thus in this example, if we can see that the entries in the third row. So, synthetic division is based on Horner's method. As a consequence of the polynomial remainder theorem, the entries in the third row are the coefficients of the second-degree polynomial. The quotient of on division by the remainder is 5. This makes Horner's method useful for polynomial long division. Divide by 2 1 6 1 1 6 2 8 6 1 4 3 0. The quotient is Latin. Divide by using Horner's method. 2 4 6 0 3 minus 5 1 2 2 1 1 2 2 1 1 minus 4. The third row is the sum of the first two rows divided by 2. Each entry in the second row is the product of 1 with the third row entry to the left. The answer is floating point multiplication and division. Horner's method is a fast, code-efficient method for multiplication and division of binary numbers on a microcontroller with no hardware multiplier. One of the binary numbers to be multiplied is represented as a trivial polynomial, where I equals 1, and x equals 2. Then, x is repeatedly factored out. In this binary numeral system, x equals 2, so powers of 2 are repeatedly factored out. Example. For example, to find the products of two numbers, and m. Method to find the product of two binary numbers, d and m. 1. A register holding the intermediate result is initialized to d. 2. Begin with the least significant non-zero bit in m. 2b. Count the number of bit positions to the next most significant non-zero bit. If there are no more significant bits, then take the value of the current bit position. 2c. Using that value, perform a right shift operation by that number of bits on the register holding the intermediate result. 3. If all the non-zero bits were counted, then the intermediate result register now holds the final result. Otherwise, add d to the intermediate result, and continue in step number 2 with the next most significant bit in m. Derivation in general, for a binary number with bit values. So this reduces to, or equivalently. In binary math, multiplication by a power of 2 is merely a register shift operation. Thus, multiplying by 2 is calculated in base 2 by an arithmetic shift. The factor is a right arithmetic shift, a results in no operation, and a results in a left arithmetic shift. The multiplication product can now be quickly calculated using only arithmetic shift operations, addition and subtraction. The method is particularly fast on processes supporting a single instruction shift and addition accumulate. Compared to AC floating point library, Horner's method sacrifices some accuracy, however it is nominally 13 times faster form is used, and uses only 20% of the code space. Polynomial root finding using Horner's method in combination with Newton's method, it is possible to approximate the real roots of a polynomial. The algorithm works as follows. Given a polynomial of degree with zeros, make some initial guess such that. Now iterate the following two steps. 1. Using Newton's method, find the largest zero of using the guess. 2. Using Horner's method, divide out to obtain. Return to step 1 but use the polynomial and the initial guess. These two steps are repeated until all real zeros are found for the polynomial. If the approximated zeros are not precise enough, the obtained values can be used as initial guesses for Newton's method, but using the full polynomial rather than the reduced polynomials. Example, consider the polynomial, which can be expanded to from the above. We know that the largest root of this polynomial is 7, so we are able to make an initial guess of 8. Using Newton's method, the first zero of 7 is found as shown in black in the figure to the right. Next is divided by to obtain, which is drawn in red in the figure to the right. Newton's method is used to find the largest zero of this polynomial with an initial guess of 7. The largest zero of this polynomial, which corresponds to the second largest zero of the original polynomial, is found at 3 and is circled in red. The degree 5 polynomial is now divided by to obtain, which is shown in yellow. The zero for this polynomial is found at 2 again using Newton's method and is circled in yellow. Horner's method is now used to obtain, which is shown in green and found to have a zero at -3. This polynomial is further reduced to which is shown in blue and yields a zero of -5. The final root of the original polynomial may be found by either using the final zero as an initial guess for Newton's method, or by reducing and solving the linear equation. As can be seen, the expected roots of -8, -5, -3, 2, 3, and 7 were found. Octave implementation. The following octave code was used in the example above to implement Horner's method. Function yb equals Horner % input a is the polynomial coefficient vector, x the value to be evaluated at, % the output y is the evaluated polynomial, and b the divided coefficient vector. B equals a, for I equals 2, length b equals a plus x asterisk b, and y equals b equals b1, end. Python implementation. The following Python code implements Horner's method. Def Horner, a function that implements the Horner scheme for evaluating a polynomial of coefficients asterisk polynomial in x. Result equals 0 for coefficient in polynomial. Result equals result asterisk x plus coefficient. Return result. C implementation. The following C code implements Horner's method. Double Horner evaluate asterisk. We want to evaluate the polynomial in x of coefficients of polynomial using Horner's method. The result is stored in d result asterisk double d result equals 0.0 int I 4 d result equals d result asterisk x plus coefficients of polynomial I. Return d result. Application. Horner's method can be used to convert between different positional numeral systems, in which case x is the base of the number system, and the I coefficients are the digits of the base x representation of a given number, and can also be used if x is a matrix, in which case the gain in computational efficiency is even greater. In fact, when x is a matrix, further acceleration is possible, which exploits the structure of matrix multiplication, and only instead of n multiplies are needed using the 1973 method of Patterson and Stockmeyer. Efficiency. Evaluation using the monomial form of a degree n polynomial requires at most n additions and 2 multiplications. If powers are calculated by repeated multiplication and each monomial is evaluated individually. By contrast, Horner's method requires only n additions and n multiplications, and its storage requirements are only n times the number of bits of x. Alternatively, Horner's method can be computed with n fused multipliads. Horner's method can also be extended to evaluate the first k derivatives of the polynomial with knots, additions and multiplications. Horner's method is optimal, in the sense that in any algorithm to evaluate an arbitrary polynomial must use at least as many operations. Alexander Ostrovsky proved in 1954 that the number of additions required is minimal. Victor Pan proved in 1966 that the number of multiplications is minimal. However, when X is a matrix, Horner's method is not optimal. This assumes that the polynomial is evaluated in monomial form and no preconditioning of the representation is allowed, which makes sense if the polynomial is evaluated only once. However, if preconditioning is allowed and the polynomial is to be evaluated many times, then faster algorithms are possible. They involve a transformation of the representation of the polynomial. In general, a degree n polynomial can be evaluated using only multiplications and n additions. History. Horner's paper entitled "A New Method of Solving Numerical Equations of All Orders by Continuous Approximation" was read before the Royal Society of London, at its meeting on July 1, 1819, with Davies Gilbert, Vice President and Treasurer, in the chair. This was the final meeting of the session before the Society adjourned for its summer recess. When a sequel was read before the Society in 1823, it was again at the final meeting of the session. On both occasions, papers by James Ivory, FRS, were also read. In 1819, it was Horner's paper that got through to publication in the Philosophical Transactions. Later in the year, Ivory's paper falling by the way, despite Ivory being a fellow, in 1823, when a total of 10 papers were read. Fortunes as regards publication were reversed. But Gilbert, who had strong connections with the west of England and may have had social contact with Horner, resident as Horner was in Bristol and Bath, published his own survey of Horner-type methods earlier in 1823. Horner's paper in Part 2 of Philosophical Transactions of the Royal Society of London for 1819 was warmly and expansively welcomed by a reviewer in the issue of the Monthly Review, or Literary Journal for April 1820. In comparison, a technical paper by Charles Babbage is dismissed curtly in this review. However, the reviewer noted that another, similar method had also recently been published by the architect and mathematical expositor, Peter Nicholson. This theme is developed in a further review of some of Nicholson's books in the issue of the Monthly Review for December 1820, which in turn ends with notice of the appearance of a booklet by Theophilus Holdred, from whom Nicholson acknowledges he obtained the gist of his approach in the first place, although claiming to have improved upon it. The sequence of reviews is concluded in the issue of the Monthly Review for September 1821, with the reviewer concluding that whereas Holdred was the first person to discover a direct and general practical solution of numerical equations, he had not reduced it to its simplest form by the time of Horner's publication, and saying that had Holdred published 40 years earlier when he first discovered his method, his contribution could be more easily recognized. The reviewer is exceptionally well informed, even having cited Horner's preparatory correspondence with Peter Barlow in 1818. Seeking work of Boudin. The Bodleian Library, Oxford has the editor's annotated copy of the Monthly Review, from which it is clear that the most active reviewer in mathematics in 1814 and 1815 was none other than Peter Barlow, one of the foremost specialists on approximation theory of the period, suggesting that it was Barlow who wrote this sequence of reviews. As it also happened, Henry Atkinson, of Newcastle, devised a similar approximation scheme in 1809. He had consulted his fellow Geordie, Charles Hutton, another specialist and a senior colleague of Barlow at the Royal Military Academy, Woolwich, only to be advised that, while his work was publishable, it was unlikely to have much impact. J.R. Young, writing in the mid-1830s, concluded that Holdred's first method replicated Atkinson's, while his improved method was only added to Holdred's booklet some months after its first appearance in 1820, when Horner's paper was already in circulation. The feature of Horner's writing that most distinguishes it from his English contemporaries is the way he draws on the continental literature, notably the work of R. Barguest. The advocacy, as well as the detraction, of Horner's method has this as an unspoken subtext. Quite how he gained that familiarity has not been determined. Horner is known to have made a close reading of John Bonnycastle's book on algebra, but Bonnycastle's main purpose in mentioning R. Barguest is not to praise him, but to observe that R. Barguest's notation is incompatible with the approach he adopts. The gap in Horner's reading was the work of Paolo Ruffini, except that, as far as awareness of Ruffini goes, citations of Ruffini's work by authors, including medical authors, in Philosophical Transactions speak volumes. There are none. Ruffini's name only appears in 1814, recording a work he donated to the Royal Society. Ruffini might have done better if his work had appeared in French, as had Malfati's problem in the reformulation of Joseph Diaz-Gergon, or had he written in French, as had Antonio Cagnoli, a source quoted by Bonnycastle on series reversion. Fuller showed that the method in Horner's 1819 paper differs from what afterwards became known as Horner's method, and that in consequence the priority for this method should go to Holdred. This view may be compared with the remarks concerning the works of Horner and Holdred in the previous paragraph. Fuller also takes aim at Augustus de Morgan. Precocious though Augustus de Morgan was, he was not the reviewer for the Monthly Review, while several others, Thomas Stevens Davies, R. Young, Stephen Fenwick, T. Wilkinson, wrote Horner firmly into their records, not least to Horner himself, as he published extensively up until the year of his death in 1837. His paper in 1819 was one that would have been difficult to miss. In contrast, the only other mathematical citing of Holdred is a single-named contribution to the Gentleman's Mathematical Companion, an answer to a problem. It is questionable to what extent it was De Morgan's advocacy of Horner's priority and discovery that led to Horner's method being so called in textbooks. But it is true that those suggesting this tend themselves to know of Horner largely through intermediaries, of whom De Morgan made himself a prime example. However, this method qua method was known long before Horner. In reverse chronological order, Horner's method was already known to Paolo Ruffini in 1809, Isaac Newton in 1669, the Chinese mathematician Zhu Shijia in the 14th century, the Chinese mathematician Qin Jiushao in his mathematical treatise in 9 sections in the 13th century, the Persian mathematician Sharaf al-Din al-Tusi in the 12th century, the Chinese mathematician Jia Jian in the 11th century. The 9 chapters on the mathematical art, a Chinese work of the Han Dynasty edited by Liu Hui. However, this observation on its own masks significant differences in conception and also, as noted with Ruffini's work, issues of accessibility. Qin Jiushao, in his Shushu Zhuzhang, presents a portfolio of methods of Horner type for solving polynomial equations, which was based on earlier works of the 11th century Song dynasty mathematician Jia Jian. For example, one method is specifically suited to bikinetics, of which Qin gives an instance, in keeping with the then Chinese custom of case studies. The first person writing in English to note the connection with Horner's method was Alexander Wiley, writing in the North China Herald in 1852, perhaps conflating and misconstruing different Chinese phrases. Wiley calls the method harmoniously alternating evolution, working the case of one of Qin's cortex and giving, for comparison, the working with Horner's method. Yoshio Mikami in Development of Mathematics in China and Japan, published in Leipzig in 1913, gave a detailed description of Qin's method, using the cortex illustrated to the above right in a worked example. He wrote, Who can deny the fact of Horner's illustrious process being used in China at least nearly 6 long centuries earlier than in Europe? We of course don't intend in any way to ascribe Horner's invention to a Chinese origin, but the lapse of time sufficiently makes it not altogether impossible that the Europeans could have known of the Chinese method in a direct or indirect way. However, as Makami is also aware, it was not altogether impossible that a related work, See Yuan Yujian by Zhu Shijia, might make the shorter journey across to Japan, but seemingly it never did, although another work of Zhu, Suanzu Qimeng, had a seminal influence on the development of traditional mathematics in the Edo period, starting in the mid-1600s. Ulrich Liebrecht gave a detailed description in his doctoral thesis of Qin's method. He concluded, "It is obvious that this procedure is a Chinese invention. The method was not known in India." He said, Fibonacci probably learned of it from Arabs, who perhaps borrowed from the Chinese. Here, the problem is that there is no more evidence for this speculation than there is of the method being known in India. Of course, the extraction of square and cube roots along similar lines is already discussed by Lu Hui in connection with problems IV, 16 and 22 in Zhujiang, Suanshu. While Wang Xiaotong in the 7th century supposes his readers can solve cubics by an approximation method he does not specify.